Everyone, and welcome back to PLC Programming from Scratch. This is section 3, and we're going to be discussing I/O, which means inputs and outputs. When you think about the word PLC, which means Programmable Logic Controller, the name itself implies that we're going to be controlling something. The signals that our PLC sends out to control devices such as pumps and motors and valves are called outputs. The signals coming into our PLC, which tell it what's happening in the process around it, are called inputs. And one of the first things that a programmer needs to understand when they're first learning about PLCs is I/O. How do I get information into my PLC, and how do I control things around me? Without I/O, if we had an isolated PLC, it really wouldn't serve any purpose that a computer couldn't serve, and probably much better. So, by necessity, if we're using a PLC, there's got to be some signals coming in and/or some signals going out. When you look at I/O, generally speaking, you can break it down into two categories. There are discrete, also known as digital signals, and then there are analog signals. And in the next lecture, we're going to be getting into what the different types of I/O are, how do we categorize them, how do we process them, and why we need the different types of I/O. In the next section, we'll get a lot deeper into digital inputs and outputs and analog inputs and outputs. And further into the course, we'll learn the various considerations to take when programming and handling those different signals. Welcome back, everyone. As promised, it's time for us to get a little bit deeper into I/O, and we're going to start with the easiest type of I/O, and that is discrete, also known as digital devices. What we're looking at on the screen right now are a few samples, and there are limitless types of digital input devices, but some of the ones we might be more familiar with are things like push buttons, toggle switches, pressure switches, flow switches. Anything that is either on or off is a digital device. So maybe the closest thing to you right now is your light switch. You walk up to your wall and you toggle the switch. Your light bulb is either on or off unless you have a dimmer, which are kind of out of style now. There is no in between. There is no 80% illumination. Your light is on or it's off. Those are the type of signals that account for most of what we'll usually be programming in the field, although I'm sure there are those exceptional projects where everything is analog. But these signals, when we're talking about a program and we're talking about logic, they're described as being either 1 or 0 when you look at the register in the memory and the data table inside of the PLC. But we also hear them described as being on or off, true or false, open and close, black or white. These devices are one of two states at any time, and that makes it so simple for programming. Just as we have digital inputs coming in, you can imagine we also have digital signals going out to control devices that also work on Boolean terms. As examples on the screen, we have a couple of relays, we have an actuated valve, and we also have a single speed pump. Any one of these devices gets a signal from a PLC that says energize, actuate, start, or it says de-energize, go the other way, or stop. It's one or the other, black and white, and we love that kind of programming. Okay, as promised in the last lecture, we are back and we're going to discuss the second half of inputs and outputs. These are our analog devices. If you remember from our discussion of digital, those devices send a signal of 0 or 1, open or closed, energized or de-energized, very clean, very simple. Analog devices are nothing like that. Analog signals come in a range expressing various levels of precision. Some of those ranges include 4 to 20 milliamps, 0 to 5 volts, negative 10 to positive 10 volts, 0 to 10 volts. There's all kinds of different analog signals that you can work with. There are variable frequencies, but typically for a PLC, you're going to work with either milliamp signals or DC voltage signals. And when you look at something like a 4 to 20 scale, that signal can be 4.28 milliamps, it can be 16.37 milliamps. There are a lot more possibilities with analog devices than what you have with digital. So it makes programming, it makes controlling a lot more interesting, and there are a lot more considerations along the way. One of the things that we're going to look at in section 5 is resolution. How precisely can we read a signal, or how precisely can we control an analog device? So stick around. It's a little bit complicated now. It will get more so. Alright, before we move into our next section and start talking about actual programming, there's one last topic I want to mention in I/O, and that is I/O modules. When you buy a lower end PLC, it typically comes with a few channels of input and a few channels of output, sometimes even both analog and digital. And you can take that PLC and drop it right into a project, load it with a program, and you're ready to go. But when you buy the more sophisticated PLCs, they typically come with no I/O whatsoever, and you have to add on modules in order to receive signals or send signals out. And the modules come in all different shapes and sizes depending on the type of PLC and the manufacturer that is behind it. And there are very general modules that handle simple digital inputs and digital outputs, and there are also some more specialized modules specifically geared to RTD signals, thermocouple signals, high-speed inputs that have to be read at a much higher frequency than a typical module can handle. There are several different kinds of modules, and there are even generic modules that can attach to several different types of PLCs through Ethernet communication protocols and things like that. So there is a world of I/O modules out there, and we're going to be working with a couple and configuring them in the next section. So I figured it was pretty important to introduce you to this concept. But by using modules instead of PLCs having everything all-inclusive, the PLCs are very scalable. If you need a system that only has 20 channels of I/O, you don't have to pay for 300 channels. However, if an existing project needs to add a few devices and you're called out to the retrofit, you don't have to install a brand new PLC. As long as you have room on your DIN rail, you can probably just add 1 or 2 more modules and keep everything exactly the way it is. So all in all, it's a good system. Okay, that was a ton of information about I/O, inputs and outputs. You've got all these different I/O modules that can connect up to your PLC. You've got analog signals, digital signals, signals coming in, signals going out. And let's not even start talking about scaling. You have all these different sensors that have all these different ranges of what they can measure, and then those ranges get converted into other ranges by our modules, and then we scale those ranges into other ranges for display and to run PIDs and things like that. Man, I/O seems like a big, complicated, scary, intimidating, nasty kind of thing. But really, this is not something you're actually going to struggle with in the field. When it comes right down to it, you've got your digital stuff, right? Digital signals going in and going out. It's just on or off. It's just a light switch, folks. That's all there is to it. You've got good digital control logic that you're going to be using to control your output devices, your digital output devices, and that is going to take care of all you really need to know about digitals, honestly. The signals coming in, it's either high or low, easy. The signals going out, you either use proper programming to control it and it's only one circuit, or you're going to have a hard time. When it comes to our analogs, that's when there's a little bit of math involved. That's when you've got these different ranges. But I want you to think about this, really simply, right? You've got different kinds of electrical signals coming in. Maybe we have a 4 to 20 milliamp signal or a 0 to 10 volt signal, or maybe we have a thermocouple or something like that, and they're all sending different types of electrical signals in. As programmers, we really don't care about what kind of signals coming in because our module is going to handle that for us. We're going to tell the module, first we're going to buy the right kind of module, and then we're going to configure that module for the signal that's coming in. And once it's all said and done, when it gets to the program, all we get is a number. We don't know or care if it was once upon a time milliamps or volts or millivolts or whatever. It's just irrelevant to us. When it comes into the program, it's a number on a range, right? It's that simple. It's a number from 0 to 100, or it's a number from 0 to 16,383, or it's a number from 4,000 to 20,000. Does it really matter what the range is? I mean, if I told you I was going to invent a new scale and it was going to be from 100,000 to 160,000, does it matter? It shouldn't, because if I give you a number, you still know enough basic algebra to figure out, is that 10% up the range or 20% up the range, or is it 90% up the range? And then wherever that is, we can say, oh, well, that's 70% or 30%. And we know how to work with that number mathematically. Basic algebra, right? This is stuff you were learning in school when you were like 12 or 13 years old, something like that. So really, when it comes to I/O, that's all there is to it. Buy the right module and set it once and it's done. And from then on, all you have to do is deal with numbers if it's analog. If it's digital, it's even simpler than that, right? Coming in, we just look to see, is it on or is it off? Is it open or is it closed? And going out, we either set it or we unset it. It's either 1 or it's 0. That's it. So don't let all these different number ranges and modules and filters and settings, don't let all of that intimidate you, because it looks like a lot, but when you're actually working with it in the field, it ultimately, it's about 5 or 10 seconds worth of setup, and then the programming for the analog, it's just basic algebra. It's just a number along a range of numbers. That's all it ever is. That's where you spend your time. And once you know how to scale, once you've learned basic scaling, It doesn't matter that the range changes. It doesn't matter that it's a different sensor type. It doesn't matter that the signal's going in or coming out, because really, once you learn how to scale, it's all the same. So don't get intimidated by I/O. There's really nothing to it. When you get in the field and you're working with it, it's just that simple. It's basic algebra and 5-10 seconds worth of setup. That's it.